Welcome to our session on quantum many-body fermionic Hamiltonians. Today, we are going to focus on quantum many-body systems that are made of fermions. And in particular, we are going to understand what is the difference between single particle and quantum many-body fermionic systems. We will understand how we can compute expectation values and how we can use these expectation values to learn about what is the ground state of our quantum many-body Hamiltonian, in particular to see phase transitions in fermionic systems. Let us start by understanding how can we go from single particle Hamiltonians to many-body Hamiltonians for fermions. And for this, let us start with the simplest model for an interacting fermionic system. So we are going to consider two sites. So site number 0 and site number 1, and there's going to be a hopping between site number 0 and site number 1, and of course the Hermitian conjugate. And apart from this, we are going to consider that there's some quantum many-body interaction. This is a term that makes the Hamiltonian intrinsically many-body, namely that we no longer have only bilinear terms in the Hamiltonian, but we also have biquadratic terms in the Hamiltonian. And you can understand that this term is a density-density interaction. So charge density in site number 0 and charge density in site number 1. One way of solving this fermionic quantum many-body Hamiltonian is taking a basis for the quantum many-body space and writing the Hamiltonian in that basis. And in particular, if we only have two sites, the basis that we would have has 4 different states. There's the state that it's what we call the vacuum state that has no electrons whatsoever. So we have the 2 levels, but both levels are empty. Then there's a state where we have 1 electron in the first level, but no electron in the second level. Then there's another state where we have 1 electron in the second level, but not in the first one. And then we have the last level where we have electrons in both levels, in the first one and in the second one. And you can think that these vectors essentially form a basis of the many-body Hilbert space. And in this basis, you can write down this Hamiltonian as a matrix. That since our basis is 4-dimensional, our Hamiltonian is going to be a 4x4 matrix. We can now consider a slightly more complicated case. So let us imagine that instead of having 2 levels, we now have 3 levels. And for 3 levels, we would write an analogous Hamiltonian. So we would have hopping between the levels and then many-body interaction between the levels. And now that we have this Hamiltonian for 3 levels, we need to again choose a basis and write the Hamiltonian in this basis. And if we have 3 levels, all the elements of the basis are shown over here. So we have the element that has no electrons, elements that have 1 electron in one of the 3 levels, like this one, and that one. We also have states that have 2 electrons in different levels, like this one over here, this one over here, and this one over here. And finally, we have a state that has all the electrons filled, which is this one that appears over here. So if we have 3 different levels, we will have 8 states that form the basis of our many-body Hilbert space. And in particular, you can keep doing this game over and over and over. And if you go to, let's say, bigger system sizes, you can very easily see that the number of states that you need to generate the whole Hilbert space grows exponentially with the number of single particle levels. So for 2 levels, you have 4 states, so 2 to the 4. For 3 single particle levels, we in total have 8 many-body states, so 2 to the 3, and so forth. If we only focus on states that have just 1 electron, like this one over here, this one over there, and this one over there, then the dimensionality of the basis just grows linearly with the system size. And this is the case for single particle electronic systems. So in single particle systems, we essentially write down the full Hamiltonian in the basis of single particles. And that's why for L sides, we have a matrix that it's an L times L matrix. But if we have quantum many-body Hamiltonians, and in particular, we have terms in our Hamiltonian that are not bilinear, but rather biquadratic, then we need to write the whole Hamiltonian in this full basis. And when we do this, we get that the Hamiltonian is a matrix that is 2 to the L times 2 to the L. And so once we have this Hamiltonian written in the many-body basis, that in general is going to be this exponentially large matrix, we can find the many-body ground state. And the many-body ground state is, of course, going to be a linear combination of the different elements of the basis. So we are going to have a set of coefficients, and each coefficient is going to multiply one of the states of the basis. So each one of these states of the basis are the states that we showed before. And in particular, we want to compute the ground state, we need to determine 2 to the L coefficients. So an interacting quantum many fermionic system, it is as challenging to solve as a spin Hamiltonian, as a quantum spin Hamiltonian. And in particular, one can think that when dealing with fermionic systems, we can have two different types of fermionic sites. The type of fermionic site that we discussed before is the spinless fermion case. So we consider that in each level, we can either have 0 electrons or 1 electron. So we can have the state either empty or filled. Of course, if we assume that our electrons also have spin degree of freedom, then in each level we could put an up electron or a down electron. One way of thinking about spin is to consider that spin is just another level. So instead of having, let's say, one level per single particle level, we now have 2 levels per single particle level. And so if you have spin-full electrons, your growth of the Hilbert space is still exponential, but twice as fast as if you have spinless fermions. And then, of course, we also saw that quantum spin models have a very similar exponential growth of the Hilbert space. And in particular, you can actually see that the growth of the Hilbert space for spins is as fast as the growth for spinless fermions. And this kind of motivates you to think that perhaps spinless fermionic Hamiltonians and spin Hamiltonians are actually similar to each other and that there's a mapping between each other, and that is actually the case. That's something that we will discuss later on. But for us, what it's important to note is that solving an interacting spinless fermionic Hamiltonian is as challenging as solving a quantum spin model, and of course solving spin-full fermionic systems is twice as challenging in an exponential sense in comparison with spinless fermions. Okay, let us now move on to look at a few simple fermionic many-body Hamiltonians. And in particular, we will see how we can understand phase transitions just by directly looking at the fermionic many-body spectra. So if we take one fermionic Hamiltonian like the one that we considered before, so a one-dimensional chain with first neighbor hopping and density-density interaction between first neighbors, the first thing that you see is that once you compute the eigenenergies of the fermionic Hamiltonian as a function of the system size, you see that as you make the system bigger and bigger and bigger, you get more and more eigenenergies. This is very similar to what one observes with quantum spin models, and this is related with the exponential growth of the Hilbert space that in particular gives rise to an exponential growth of the eigenenergies of the Hamiltonian. If we can look at this model a little bit more in detail. So if we consider this one-dimensional chain with first neighbor hopping and interactions between first neighbors, now I am adding here this term -1/2 to force the system to be half-filled in the absence of a chemical potential. What we can actually see is that this model has two relatively simple limits. The first limit corresponds to when V is equal to 0. So in this case, the system is metallic, so we have a single particle model. We have just a one-dimensional chain with hopping. And in this case, the system is a metal because electrons are not interacting with each other. If we consider V equal to infinite, we can effectively just ignore this term in the Hamiltonian and consider that our full Hamiltonian is this term over here. And if your full Hamiltonian is just this term that you have on the right, you can actually easily see that the ground state that you get is a ground state where you have 1 electron in one side and 0 electrons in the next one, and then 1 electron and 0 electrons, and then 1 electron and 0 electrons, because that's actually the state that minimizes the energy of that Hamiltonian. And it's an eigenstate of the Hamiltonian because you no longer have hopping. If you have both hopping and interaction, there's going to be at some point a phase transition between these two states. So the question that we want to answer is, how can we see such a phase transition? And to answer this question, what it's important to note is that in this limit, in the limit where V is equal to infinite, we actually have two ground states in the thermodynamic limit. We have one ground state where we have 1 electron over here and 0 electrons over there, but then we have the opposite ground state, which is where we have 0 electrons in this side and 1 electron in this side. Whereas in the metallic state, there's only a single ground state. There's a single state with the lowest energy. And this difference in the number of ground states that we have is what allows us to see phase transitions. So in order to do this, what we are going to do is we take a chain that it's finite, because we need to solve this exactly using diagonalization, and we will look at the eigenvalues as a function of the interaction. And in particular, we are going to look at the eigenvalues as a function of interaction for two different system sizes. So if you look first at the eigenvalues for V equal to 0, and here I am removing the contribution from the ground state energy so that the ground state is always at 0. What you actually observe is that for V equal to 0, you have a single ground state, and then there's a finite gap. And this gap is actually a finite size gap. What this actually means is that as you make the system bigger and bigger and bigger, this gap becomes smaller and smaller and smaller, and eventually you obtain a continuum of states over here that correspond to your metallic states in the non-interacting limit. If you now start increasing the value of the interaction, what you actually observe is that when you go to very large interactions, suddenly there's another state that gets very, very close to the ground state. And you can actually see that if you go to arbitrarily large interactions, it actually gets the same energy as the ground state. So at large interactions, your ground state is no longer singly degenerate, but it becomes twofold degenerate. And this twofold degeneracy that appears at large interactions is actually the twofold degeneracy associated with the charge density wave order that appears at large interactions. What it's interesting to do is to actually compare the evolution of these eigenvalues for two different system sizes. So if you make the system a little bit bigger, what you actually observe is that this approach of this first excited state to the ground state happens a little bit sooner. What this actually means is that if you keep making the system bigger and bigger and bigger, you can actually expect that then every time the state is going to get closer to the ground state sooner. And what it's also important is that, of course, as you make the system bigger and bigger and bigger, the states over here are going to get closer and closer, which, of course, is related with the fact that states at V equal to 0 give rise to a metal. So eventually, in the thermodynamic limit, you would expect a continuum of states over here. Something that is also interesting to note is that whereas at V equal to 0, you have a continuum of states close to the ground state, and it will become more continuous in the thermodynamic limit. If you go at large V, you actually get a very large gap. You have a very wide region in energy where there's no state between the ground states and the first excited state. And this happens both for L equal to 12 and L equal to 14. And if you look at what is the slope of this state, you can actually see that the slope is approximately V, especially for very large V. So what this is actually telling you is that in the thermodynamic limit, this is going to be an insulator. You're going to have a ground state that is twofold degenerate, and then a huge gap that is proportional to V, and it's going to become insulating. we can understand a little bit more what is the nature of the insulating state in the strongly interacting limit if we add a chemical potential to the Hamiltonian. So we can consider the same Hamiltonian as before. We have kinetic energy, which is the hopping between electrons in the one-dimensional chain. Then we have our interaction, which is the density-density interaction between nearest neighbors in the chain. And then we add the chemical potential, which is in practice a term that counts how many electrons we have in the system. Something that it's important to note is that this chemical potential actually commutes with the Hamiltonian, meaning that this term over here, if you compute the commutator with the rest of the Hamiltonian, is zero. And what this actually means is that it does not modify the eigenstates of the Hamiltonian, but it only modifies the eigenenergies. Or in other words, one can find a common basis between this original Hamiltonian and the number operator, where both the number operator and the Hamiltonian are diagonal. So if we go to this large interacting limit, what we actually observe is that first there's a gap between the ground state, or actually ground states, and the first excited state. And then as you increase the chemical potential, what actually happens is that such a gap becomes smaller. So there's an excited state that goes linearly towards the ground state, and then another excited state that goes linearly towards the ground state, and then there's an excited state that actually gets higher energy as you increase the chemical potential. And this is actually easier to see if you compute what is the expectation value of the number operator for every single state in the system. So this is effectively just the number of electrons that each many-body state has. And for convenience, we can just plot the number of electrons minus the total length of the system over 2, so that for our ground state, we get a value of 0. And we can look at what is the extra number of electrons with respect to the ground state that our excited states have. So if our ground state is over here and has an excess of 0 electrons with respect to the ground state, then as we use positive or negative chemical potential, we get that there are excited states that become closer to the ground state, but they have a completely different number of electrons. So this excited state has one less electron than the ground state, and this excited state has one more electron than the ground state. What this actually means is that when you put a positive chemical potential, effectively it is easier to remove one electron, and when you put a negative chemical potential, it is easier to add one electron. And this is, of course, something that it will become very important if your chemical potential is very, very large. And in particular, if your chemical potential is stronger than the quantization energy that appears due to the finite size of your system and the kinetic energy and the many-body interaction. So if you ramp up the value of the chemical potential, you can actually see that at your chemical potential, you have the original ground state, and eventually the ground state switches, and you get a ground state, a state that has one less electron than the original one. And then if you keep increasing the chemical potential, then you have another switch of the ground state, and you have a new ground state that has 2 less electrons than the original one. So what is actually happening here is that the chemical potential is capable of controlling the number of electrons that your ground state has. Here you are half filled, here you are half filled minus 1 electron, here you are half filled minus 2 electrons. And of course, if you go to the opposite chemical potential, you get the opposite behavior. So here you are half filled, here half filled plus 1 electron, here half filled plus 2 electrons, and so forth. So the chemical potential not only changes the distance between the ground state and the excited states, but it is also capable of changing who is the ground state if it is large enough. And in particular, this is something that one can systematically look at as a function of the interaction of the system. So what we are showing here is the occupation number as a function of the chemical potential for 2 different interaction strengths. So if we start first at zero chemical potential, what we actually have is that every single site is half-filled. And as we increase the chemical potential, we see that at a certain chemical potential, we get an additional electron that goes to some single particle state or something that looks like a single particle state. And then if we keep increasing the chemical potential, then we get more electrons and the more and the more, and eventually it saturates. So when we are at this chemical potential, we effectively have all the electrons that are possible in our system. So every single site has filling 1, and we cannot put more electrons in the system. And a similar behavior happens if you use negative chemical potential instead of positive. So of course, once the chemical potential is small enough, then you actually get a system that is completely empty. You can do the same with a stronger interaction. And what you observe when you use a stronger interaction is that actually, in order to completely fill your system or completely empty the system, you need to use larger chemical potentials. And if you look at the energy spacing or at the interval of chemical potentials where you have a certain number of electrons stabilized, you see that for stronger interactions, it is bigger. So you have to compare this width in chemical potential with this width in chemical potential over here. And this difference in the chemical potential that one needs to add as a function of the interaction is what it's called the charging energy. So the stronger your many-body interactions are, the more you have to push the chemical potential in order to add or remove electrons, because you have to win over the charging energy of the system. Okay, so far we have been focusing on a spinless fermionic model. We can now use very similar ideas in order to understand the physics of a spinful fermionic model. And in particular, the most important spinful fermionic model is the Hubbard model. And it is especially important because we will see that the Hubbard model actually behaves in a certain limit like the Heisenberg model. Okay, so the Hubbard model is a relatively simple model. So we take spinful electrons. So we take a one-dimensional chain with hopping, where we have hopping between electrons with same spin and between nearest neighbors. So this is the C dagger NS Cn plus 1s. And then we have a local interaction. And this is a local Hubbard interaction, which can be understood as a density interaction. And this minus 1/2 over here is added just to ensure that the system is half-filled without any additional chemical potential. If you just do the algebra in this term, you can see that this minus 1/2 just transforms in a chemical potential. And the first important thing that one can do is to compute the ground state of the system for a certain system size and the expectation value of the magnetization. And if you do that, what you actually observe is that even in the limit of very, very strong interactions, the magnetization is exactly 0 in every single site. And this is actually very surprising, at least if you come with the mindset of mean field theory. Because if you take this original Hamiltonian and solve it with mean field theory, you would obtain that the ground state has a finite magnetization. It has a magnetization that oscillates between sites. So you get positive magnetization for even sites and negative magnetization for odd sites. And mean field calculations are always going to give rise to a ground state that has a magnetization if interactions are strong enough. But the actual and real ground state of the Hubbard model is a ground state that has 0 magnetization everywhere. And this is something that can be actually rationalized by solving the exact many-body Hamiltonian. So let us now slightly modify the Hubbard model so that we, in a way, interpolate between the true Hubbard model and what we believe would be the mean field solution of the Hubbard model. So we are going to still consider kinetic energy and many-body interaction, and in particular the Hubbard interaction, but now we are going to add this extra term that it's a stagger magnetization, a mean field stagger magnetization. So this term at the end is effectively the single particle term that you would have gotten if you solved the Hubbard model using mean field theory. So in particular, if you remove this term over here, if you remove the many-mode interaction, you can think that kinetic energy plus the staggered magnetization is effectively the mean field Hamiltonian that you would have gotten. And for our purpose, let us just solve this full Hamiltonian, and let's look at what is the solution of the Hamiltonian as a function of the strength of the staggered magnetization. If the staggered magnetization is 0, we recover our original Hubbard model. If the staggered magnetization is very large, we are actually going towards the limit that we would have gotten if we did mean field theory. So if we consider first staggered magnetization equal to 0, which is this line over here, what you observe is that the magnetization is 0. This is the very same result as in the previous slide. And now, as you increase the value of the staggered magnetization, what you observe is that magnetization slowly starts to appear, but it actually doesn't appear suddenly. You have a slow growth of the expectation value of the magnetization on each side. So the way to understand this is that this system actually has spin correlations, antiferromagnetic spin correlations, but quantum fluctuations are actually destroying the order. And this staggered magnetization is, in a way, trying to fight the quantum fluctuations. And of course, once the staggered magnetization is very large, then quantum fluctuations no longer matter. But if it is relatively small, then quantum fluctuations are still capable of creating disorder in the system, and in particular of giving rise to a very small magnetization, and of course exactly zero magnetization if you don't have any staggered magnetization at all. Something that is very important is to understand what the excited states of the Hubbard model are, in particular in the case where interactions are very large. So what we can actually do to rationalize this is to take, again, our Hubbard model and now modify it in a slightly different way. So now what we are going to do is we are going to add a net magnetic field to the Hamiltonian. And something that is important about this term that we have here is that this operator commutes with the Hamiltonian. Or in other words, if we compute the commutator of this term over here with these other two terms over there, we get 0. And this implies that there's an eigenbasis that it's common for this total spin operator and the original Hamiltonian. And therefore, when we add this term to the Hamiltonian, we are not modifying the eigenvectors, but we are only modifying the eigenenergies. And for the sake of concreteness, we can do this for a system with two sides because it is much easier to understand. So if we start with the case phi set equal to 0, we have effectively one grounded state and then 3 excited states. And as you increase the value of the external magnetic field, what you observe is that these 3 excited states, they split, and you get a splitting that is linear with the magnetic field. And what is most important, if you compute the expectation value of the spin operator, you obtain that you have one excited state with a spin -1, one excited state with spin 0, and one excited state with a spin +1. So in other words, if you start doing excitations from the grounded state to an excited state, you have excitations that have spin 1 and excitations that have spin -1, which is what we call a magnon in the system. So in practice, this is very, very similar to what happens in the Heisenberg dimer. In the Heisenberg dimer, we also have a single grounded state and 3 excited states, which is what we called the triplet state. And if you look at the evolution of the eigenenergies as a function of the magnetic field, you see actually an evolution that is very, very similar to this one. So this type of evolution of the excited states in the Hubbard model is already telling you that you have very similar physics to the Heisenberg model. And there's something also interesting to check, which is related with the gap between this singlet and triplet state as a function of the length and the interaction of the system. So in general, we expect that as we make the system bigger and bigger and bigger, then gaps become smaller, because usually when our system is finite, we have confinement gaps. And when we go to the thermodynamic limit, some of those confinement gaps go to zero. If the system is metallic, some of those confinement gaps will go to a finite value if the system has some many-body gap. And in particular, we can do this for different values of the interaction. So we consider U equal to 0. We see that our many-body gap is decreasing as the system becomes bigger and bigger and bigger. And in this case, we know that the decrease is going to follow a power law, because for U equal to 0, our system would be a single particle system. And in particular, we would get a gap that goes as 1 over L, where L is the length. Then if you add interaction to the system, what you actually see is that the gap also decreases with length. But what is most interesting is that the gap is actually smaller when you put interaction than when you don't have interaction. If you put an interaction even bigger, you see that the gap becomes even smaller, which in a way it's quite counterintuitive, because we would expect that the Hubbard model is a model of an insulator. And if you look at this plot alone, you would actually think that your interaction is decreasing gaps and in a way making your system more metallic. The reason for this counterintuitive behavior is that what you are actually seeing here is not the charge gap, but it's the spin gap, which is very similar to what we discussed in the previous slide. So these gaps that you are observing here are the gaps between the singlet and the triplet, which, since you have a Heisenberg model, in the thermodynamic limit, they will become arbitrarily small. And in particular, the system is going to become a gapless in the spin sector, but of course you're going to have a gap in the charge sector. But this is something that will be much easier to understand later on. Okay, let us see how the system is actually an insulator, and an insulator in the charge degree of freedom. And to see that the system is insulating the charge degree of freedom, what we can do is to look at the non-local particle-particle correlator. In a way, this measures what is the probability of injecting a particle inside I and measuring it inside J. If you have an insulator, when you inject a particle inside I, then the probability of seeing it inside J is going to get exponentially suppressed. If you have a metal, there will be some probability to see it inside J. Of course, the further you are, the less probability, but the decrease is going to be much slower than exponential, and in particular, it's going to be a power law. So if you look at what is the functional form of this object as a function of distance, you can actually distinguish between a metal and an insulator. And the advantage of this non-local correlator is that this only requires the ground state. You don't need to look at excitations. You only need to take the ground state and compute this very specific expectation value. So we will be expecting that for a metal, we have a power law decrease. And for an insulator, we are going to get this exponential decrease. And this term over here in the exponential is going to be bigger, the bigger the gap is. So let us do this for the Hubbard model. So we are going to look at the particle-particle correlator between the first site and the site number J, and we'll do it for different values of the interaction. So if we take first 0 interaction, which corresponds to the single particle limit, what you observe is that there's an oscillation of this correlator. The oscillation becomes smaller and smaller as you go further and further, but there's still a probability to see the electron a little bit far from where you injected it. If you now add some finite interaction, now you see that the probability becomes smaller, but still it's possible to see the electron close to where you injected it. And if you use a very large interaction, like U equal to 10, what you actually observe is that the probability of seeing the electron very quickly goes to 0, and in particular, it goes to 0 exponentially fast. So for this plot over here, in particular for the case of u equal to 10t, you can easily see that the Hubbard model I have filling in large U is an electronic insulator, just because this non-local correlator goes to zero very quickly. That was for the charge degree of freedom, but for the spin degree of freedom, the story is very different. For the spin degree of freedom, we are actually going to have a gapless system. And this is very easy to understand if you recall the mapping between the Hubbard model in an arbitrary lattice and the Heisenberg model. So if you started with a Hubbard model that has some hopping between sites in a certain local interaction, one could map this whole model to the Heisenberg model, Jij, where Jij is effectively just the hopping to the second power over the interaction. So from this formula, you can actually observe two very important phenomena. First one is that if you have very large interactions, the system is going to effectively be gapless in the thermodynamic limit because the Heisenberg model is going to be gapless. And the second one is that the bandwidth of your spin excitations is going to decrease as 1 over u. What this actually means is that in a finite system, the singlet triplet transition is going to go as 1 over u. So the bigger the interaction, the smaller the spin gap in your system, which is the phenomenology that we observed before. With this in mind, we can now compute the non-local spin correlator in the Hubbard model. So we take different values for the interaction, and we see what is the spin fluctuation inside J with respect to site I. So if you start with U equal to 0, you see that there's a certain non-local correlation that oscillates and goes to 0 in a power law fashion. And if you start increasing U, what you actually observe is that the spin fluctuations increase. So they keep oscillating, but the value of the non-local correlator becomes bigger. So what this actually tells you is that interactions actually enhance spin fluctuations here. And they enhance spin fluctuations at the same time as they decrease charge fluctuations. So in a way, interactions are acting in two completely different ways, in the charge and in the spin sector. In the charge sector, they are completely quenching the correlations, whereas in the spin sector, they are enhancing the correlation. So you can very easily see this just by looking at these 3 points here. As you make the interaction bigger, then the fluctuation becomes bigger. And this is something that it's especially easy to see if one looks at the dynamical correlators for a spinful model. In particular, we can define two different types of correlators for spinful fermions. We can define a dynamical correlator that tells us about the spin excitations, about the spin fluctuations. So we take the ground state, we create a spin excitation, delta function with all the excited states and another spin excitation. Or you can do the same, but with charge excitation. So instead of putting a spin operator over here, you put a charge operator over there, a particle operator over there, and then the Hermitian conjugate over here. And then this allows you to see the dynamical particle correlator. One way of thinking about these two quantities is that this is the many-body generalization of the density of states. So if you had a single particle system, this would simply be the density of states, whereas this is the spin structure factor. This effectively allows you to see spin 1 excitations in the system. And in practice, what you can easily understand is that these two objects are going to be non-zero once you have a very specific excited state that has one more electron than the ground state or one more spin excitation than the ground state, depending on what is the operator that you consider there. Okay, so now let us look at this charge and spin correlator for the Hubbard model. So we are going to take the Hubbard model at a very specific value of the interaction. So U equal to 60. This is a value where the system is already very correlated and it's in the strong coupling limit. And if you look at the charge correlator, what you actually see is that there's a huge gap in the charge correlator. And if you keep making U bigger and bigger and bigger, you will observe that these peaks are going to drift to higher and higher energies. So these peaks over here, you can think that they are the peaks corresponding to the energy that you need to inject to the system in order to put one extra electron. So of course, the bigger the U, the more energy you will need to put into the system. If you look at the spin correlator, what you actually observe is that the energies at which you have a non-zero value of the spin correlator are much, much smaller than those of the charge correlator. And in particular, you see that as you make U bigger and bigger and bigger, these energies would get lower and lower and lower. And in particular, if you have this relatively large value of U, you have spin excitations that are relatively close to the ground state. And if you compare with the spin excitations of the Heisenberg model, you would see that they have a very, very similar profile. And of course, this is related with the fact that the spin excitations in the Hubbard model are effectively the same as the spin excitations in the Heisenberg model if U is very large. Another way of looking at this is just by looking at the charge and spin excitations as a function of the interaction. So if you look at the charge excitations for increasing interaction, what you actually observe is that a certain single particle peak, so you could think that this is the single particle density of states, goes to higher and higher energies as you increase the interaction. So this increase is actually linear with U, and it would become bigger and bigger and bigger as U becomes bigger, because of course this corresponds to the charging of the system. If you now look at the spin excitations, what you observe is actually the opposite behavior. So you start with an excitation at a finite energy, and then as you increase U, then the excitation goes to lower and lower energies. And in particular, it goes to lower energies as 1 over U. This behavior that you see here is very much like the behavior that you saw in the previous plot. The energy of the first charge excitation gets bigger as U becomes bigger. The energy of the first spin excitation gets smaller as U becomes bigger. And this dramatic difference in the behavior between the charge excitations and the spin excitations, it's what it's called spin-charge separation. When we have electronic interactions in a spin-full fermionic system, charge information, spin information can have completely different behaviors. And in particular, in this system, charge behaves like an insulating property, namely that in the thermodynamic limit, it would be very hard to push electrons through the system, whereas the spin fluctuations are going to remain gapless, and it will be very easy to transmit spin information in the system.